Photosystem II is the first protein complex in the light-dependent reactions of oxygenic photosyntheses. It is located in the thylakoid membrane of plants, algae, and cyanobacteria. Within the photosystem, enzymes capture photons of light to energize electrons that are then transferred through a variety of coenzymes and cofactors to reduce plastocyanin to plastocyinol. The energized electrons are replaced by oxidizing water to form hydrogen ions and molecular oxygen. By replenishing lost electrons with electrons from the splitting of water, Photosystem II provides the electrons for all of photosynthesis to occur. The hydrogen ions generated by the oxidation of water help to create a proton gradient that is used by ATP synthase to generate ATP. The energized electrons transferred to plastocyanin are ultimately used to reduce NADP+ to NADPH or are used in cyclic photophosphorylation. Structure. The core of PSII consists of a pseudo-symmetric heterodimer of two homologous proteins D1 and D2. Unlike the reaction centers of all other photosystems which have a special pair of closely spaced chlorophyll molecules, the pigment that undergoes the initial photo-induced charge separation in PSII is a chlorophyll monomer. Because the positive charge is not shared across two molecules, the ionized pigment is highly oxidizing and can take part in the splitting of water. Photosystem II is composed of around 20 subunits as well as other accessory, light-harvesting proteins. Each photosystem II contains at least 99 cofactors, 35 chlorophyll, 12 beta-carotene, 2 pheophytin, 2 plastocyanin, 2 heme, 1 bicarbonate, 20 lipid, the Mn, 4 Ca, 5 cluster, and 1 non-heme Fe2+ and 2 putative Ca2+ ion per monomer. There are different crystal structures of photosystem II. The PDB accession codes for this protein are 3W2, 3PZ1, 3PZ22AXT, 1S5L, 1W5C, 1ILX, 1FE1, 1IZL. Oxygen evolving complex. The oxygen evolving complex is the site of water oxidation. It is a metallo-oxo cluster comprising 4 manganese ions and 1 divalent calcium ion. When it oxidizes water, producing oxygen gas and protons, it sequentially delivers the 4 electrons from water to a tyrosine side chain and then to P680 itself. The structure of the oxygen evolving complex is still contentious. The structures obtained by X-ray crystallography are particularly controversial, since there is evidence that the manganese atoms are reduced by the high-intensity X-rays used, altering the observed OEC structure. However, crystallography in combination with a variety of other spectroscopic methods such as EXAFS and electron paramagnetic resonance have given a fairly clear idea of the structure of the cluster. One possibility is the Cuban-like structure. In 2011 the OEC of PSII was resolved to a level of 1.9 angstroms, revealing 5 oxygen atoms serving as oxo bridges linking the 5 metal atoms and 4 water molecules bound to the Mn4Ca5 cluster. More than 1,300 water molecules were found in each photosystem II monomer, some forming extensive hydrogen bonding networks that may serve as channels for protons, water or oxygen molecules. Water splitting. Photosynthetic water splitting is one of the most important reactions on the planet, since it is the source of nearly all the atmosphere's oxygen. Moreover, artificial photosynthetic water splitting may contribute to the effective use of sunlight as an alternative energy source. The mechanism of water oxidation is still not fully elucidated, but we know many details about this process. The oxidation of water to molecular oxygen requires extraction of 4 electrons and 4 protons from 2 molecules of water. The experimental evidence that oxygen is released through cyclic reaction of oxygen evolving complex within 1 PSII was provided by Pierre Joliot ALll. They have shown that, if dark-adapted photosynthetic material is exposed to a series of single turnover flashes, oxygen evolution is detected with typical period for damped oscillation with maxima on the 3rd and the 7th flash and with minima on the 1st and the 5th flash. Based on this experiment, Bessel-Koch and co-workers introduced a cycle of 5 flash-induced transitions of the so-called S states, describing the 4 redox states of OEC, When 4 oxidizing equivalents have been stored, OEC returns to its basic and in the dark stable SO state. Finally, the intermediate S states were proposed by Jablonski and Lazar as a regulatory mechanism and link between S states and tyrosine Z. See also: Oxygen evolution, P680, photosynthesis, Photosystem I, Photosystem II light harvesting protein, reaction center, photoinhibition. References